This is a video abstract for the paper by Liu et al. On the nature of the glass transition in 2D colloidal suspension of short rods. This work was done at the Institute for Advanced Study of Suzhou University in Suzhou, China. For 2D colloidal matter systems, if the particles are monodispersed on microspheres, the resulting phases can be a disordered glass, liquid, partially ordered hexatic, and ordered 2D crystal with quasi-long-range order. Never can one observe a glassy phase with monodispersed microspheres. When these spheres are stretched into the ellipsoid shapes, previously researchers Han et al. Have found that it is possible to create a stable 2D colloidal glass. In fact, it was found that with increasing packing density, there are two transitions into the glass phase. First, the orientational degrees of freedom got frozen, followed by the translational ones. The question is how this happened. It was proposed by previous authors. The anisotropy of the particle favors the formation of microdomains of nematics. This pseudo-nematic domains, or the jamming of them, were conjectured to be the mechanism for the glass transition. In this paper, we studied colloidal rods, stretched particles with blunt ends. We also found a two-step glass transition, even at the anisotropy as small as 1.5, for which previously in ellipsoids, no such transitions were found, and that there are no microdomains or forming. To make sense of our findings, we decided to investigate the orientational rod-rod correlation function, or GR theta. We found two favored configurations, parallel or perpendicular. We propose a kinetic model. Prior to falling out of equilibrium, the rod-rod interactions satisfy the principle of detail balance. So in other words, in the potential landscape, there were two stable local equilibrium states, parallel and perpendicular. And then so what we conjectured is that the rod-rod orientational correlation function at nearest neighbor distance is governed by the Boltzmann distribution. So therefore, we can use the BIND data to obtain a probability distribution from which we can extract the activation energy barrier. And then, so this is the result. And we found that indeed, there are two configurations that are stable. The parallel is more stable than the perpendicular one. The diagonal ones are very unstable. And then we measured the activation barrier as a function of packing density for three different anisotropies. And we found a universal behavior. And most strikingly, at the orientational glass transition, the activation energy barrier tended to a plateau. And then this plateau is the cause of the orientational glass intermediate state. So in summary, a two-step glass transition is observed in a colloidal rod system. A kinetic model is proposed in which a local activation barrier is the origin of the glass transition. And finally, we found that the barrier height versus packing density appears to follow a universal curve. Thank you.